Welcome back to CMOS radio frequency integrated circuits. We have been discussing power amplifiers. In the last class, we discussed class A amplifiers and we had started with class B amplifiers, although I do not really think we got a full understanding of what is going on. So, we are going to continue with class B, class C, class D amplifiers, and we are going to see, we are going to try to get an understanding of how to build a power amplifier. So, first of all, as we did in the previous class, previous lecture, the general picture is something that looks like this. We have a MOSFET that is amplifying a voltage. So, I am going to call this voltage, I think in the previous class I called it VRF, but let us call it V in, all right. Now, of course, there is also a bias voltage associated with the input of the MOSFET. Now, the MOSFET is powered through an RF choke. What is an RF choke? An RF choke is an inductor that is so big that it is a short as far as DC is concerned and it is an open circuit as far as RF is concerned. So, it chokes out the RF. So, it is an RF choke, and we have a DC blocking capacitor. So, I am going to call this RF choke and I am going to call this DC block. So, this capacitor is so big that it does not allow DC to go through, but it allows everything else. And then we have the load. Now, unfortunately, the circuit is going to be non-linear. We saw that we are not really planning to have a linear amplifier over here. We are just trying to blast out as much power as possible. So, therefore, I am going to put some sort of a tank circuit that is going to filter out all the other components, right, and allow the voltage at the output to be only at the desired frequency. Right. So, this is the general block, this is the general circuit diagram, and the same circuit diagram applies to class A, B, C amplifiers, A, B. So, I forgot to mention, we are also going to discuss A, B over here. So, it really is irrelevant what class we are in, this is the general picture that I have got. Now, what you have to understand is that this RF choke allows a current at DC. It does not allow current at any other frequency. It is a short circuit for DC, open circuit for AC. So, the current coming from the RF choke, it is like a constant current, no matter what mode of operation you are looking at, A, B, C, whatever you are looking at, it does not matter. The current through that RF choke is a constant current. Let us call that current I average. Okay, why I am calling it I average, we will very soon find out. The next thing to understand is that the average current through a capacitor, through the DC block capacitor, has got to be equal to 0. Okay. So, no average current flows through the DC blocking capacitor. Therefore, the drain current of the MOSFET, if I look at the average of the drain current of the MOSFET, it will be the same as I average. Let us call it I, capital I D. Okay. So, average of I D is definitely equal to I average. Why? Because no average current is going through the DC blocking capacitor anyway, right. So, therefore, the power consumption of this particular circuit, is going to be how much? The total power consumed is VDD times I average. Really, that is all there is to it. Okay. I average current is coming out of a power supply. So, the power is supplying an amount of power that is equal to VDD times I average. Does not really matter what class the amplifier is in. All right. Now, all that I need to understand is how much is the power delivered to the load, and depending upon the amount of power delivered to the load, I will be able to understand what is the efficiency of this particular amplifier. By the way, amount of power delivered to the load at the desired frequency, right. Do you agree? At the desired frequency. At other frequencies, it really does not matter what power is delivered to the load, because it is, we do not want it anyway. Okay. So, at the desired frequency, what is the power delivered to the load? That is going to give me an understanding of what is the efficiency of this particular circuit, right. Now, as we said before, we have a few definitions over here. Class A, the transistor is on 100% of the time. Class B, the transistor is on 50% of the time. And class AB, as the name is suggesting, the transistor is on for more than 50% of the time, but less than 100% of the time. All right, between 50 and 100%. So, these are the broad definitions of the different classes of the amplifiers. Now, when I say that the transistor is on for so much percent of the time, what does it mean? It means that V bias is such that for a given percentage of time, the transistor conducts current. For the remaining amount of time, this we discussed yesterday, the transistor is cut off and nothing is really flowing through the device. So, for example, let us take the example of a class B. So, this is if the current was a perfect sinusoid, but we are saying that we are going to arrange the bias voltage such that the transistor does not conduct any current for half the time. So, let us say this is 0, pi, 2 pi, 3 pi and so on, or if you want to deal with seconds, let us say the signal is at 0.5 hertz. I am sorry, let us say the signal is at 1 hertz, then this is 1 second, this is 0.5 second, this is 1.5 second and so on. All right, or if you want more general, and 1.5 times the period. So, this is the graph of the drain current. So, if this is the graph of the drain current, what is the average of the drain current? Because the average of the drain current is I average. All right. So, the average of the drain current, okay, let us first choose a maximum. Let us say this is called I max, or sure I max. Right. Integral of cos is sine or minus sine. Integral of cos is sine. Oh, we have a problem here, it is not cos. The waveform that I have drawn is not a cosine, it is a sine. So, integral of sine theta is minus cos theta, and we go from 0 to pi. So, cos pi is minus 1. So, minus of minus 1 is plus 1 and cos 0 is 1. So, minus of minus 1 minus minus 1. So, that is 2. So, my average current is I max by pi. Very interesting, right? What is interesting is that the average is over here, it is not in the middle. All right. The next thing that I need to understand is what is the power delivered. So, the power consumed is therefore I max by pi times VDD, that is the power consumed obviously, right. What is the power delivered? Now, to understand what is the power delivered, I have to find out what is the fundamental component of this current at the desired frequency. I am not interested in the other harmonics, I am interested only in the desired frequency. So, the fundamental component is you can easily distinguish where that is just by eye estimation. You do not have to work on it very hard, because think about it, how the Fourier series works. The Fourier series works, you try to place a fundamental and then you try to put a third harmonic, you try to put a fifth harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic and so on, right. So, just by eye estimation you can probably figure out that you will have a fundamental that kind of looks like this, right, just by eye estimation. I will not go into the mathematics, because I better not waste time. We will do a generalized version later on. Now, accordingly, just by eye estimation, you can see that the amplitude of the fundamental is something like I max by 2. Right, just by eye estimation. So, this is the current that is coming through the DC block, and naturally this is the current that is coming from the load, because at all other frequencies the tank is eliminating the current on the load. So, therefore, the power delivered to the load at this frequency is I max by 2 squared, is the amplitude, half of that times r, I squared r, half of I squared r, right, that is the power delivered. Now, what is this r? R antenna. Is there any relationship between R antenna, I max and the power supply? Remember now that the device cannot possibly go off, or yes, the device is going to be off right around this, from here to here the device is off, right. So, therefore, I max by 2 that is how much you have got as far as that is the amount of deviation that you have got in terms of voltage, in terms of the average voltage. So, therefore, all right, let us put it this way. If this is my VDD, if I max times R corresponds to VDD, right, then during this time frame it is going to be off. You understand what I am trying to say? If I max times R is VDD, then at this point of time, when the current is the largest, the voltage over here will be the smallest, right. You do not want the voltage, you can't allow the voltage over there to go below the saturation voltage of the transistor. Now, we assumed, made an assumption in the last class, and let us say that the minimum saturation voltage that you possibly can have is 0 volts. All right, this was a bad assumption, but nevertheless we are using this assumption for our analysis, because otherwise it is overly complicated. So, therefore, what I am trying to suggest is that at this point of time, the voltage, the signal voltage should be VDD, right, which means I max times R has got to be equal to VDD. That is my argument. Okay. I max by 2 has got to be VDD. This deviation has got to be VDD, right. So, this is basically the idea that the power delivered is VDD times I max by 4, the power that you have consumed is average current times VDD. So, therefore, the efficiency is how much? Pi by 4. Pi by 4 is something like, if you say pi is 3, then it is 0.75. Pi is a little more than 3, 3.14, right. So, it is something like 77%. So, this is basically the idea as far as class B amplifiers are concerned, and class C, this is where we will work a little harder, is a more general version of the class B, where we say that our current, let us first draw a sinusoid current. All right. Our current is positive only during this cycle, and the remaining part, the current is actually equal to 0. Okay. So, the idea is that let us approximate the current as the top portion, the crest of a sine wave, of a sinusoid. And let us say that the conduction angle, we are going to generalize this, let us say this is start of time t equal to 0, and this is time t equal to capital T, this is one period, right. Or rather, if you want to think in terms of angle, then this is 2 pi, and let us say this is phi and this is minus phi. So, it conducts when the angle is between minus phi and plus phi, or between 2 pi minus phi and 2 pi plus phi. All right. Now, once again, the thought is that the average current, I have to find out the average current, average ID, it is the same as before. So, what is the relationship between class C and class B amplifiers? So, class C is just a general version. When phi is pi by 2, I get class B. When phi is pi, I should get class A. Right. So, we will see if the same results pop out of this or not. Okay. So, here first of all I need to find out the average current. This is something that I need to find out, and the other thing that I need to find out is what is the fundamental component of ID. Okay, because this fundamental component is what is going to get delivered to the load, right. These are the two things that I need to figure out. Now, average ID is of course something like this 0 to t integral I d dt 1 by t. Why did I put 1 by 2 t? Right. Now, we are going to consider this as our 0. Now, this integral is the same as 1 by 2 pi integral minus phi to plus phi I d d theta. It is the same. Pictorially you can see that it is exactly the same. All right. So, you now all I need to understand is what is a general expression for I d. All right. So, I d is equal to 0 outside of the conduction angle. And I d is equal to some sinusoid of some magnitude, let us call this magnitude amplitude I r f, just calling it I r f. Plus, I am sorry, minus a certain quantity. So, you are downwards a certain quantity, and how much are you down by? You are down by this much, okay, or rather this much. And that is exactly equal to I r f cos phi. So, this is my mathematical expression for I d, all right, which basically means that if I want to integrate I d, if I want to find out the average I d, that is my expression. And let us work out the integral. It is not going to be terribly difficult to work out this integral. Integral of cos theta is sin theta. And integral of a constant is just the difference. Integral of a constant is the constant times theta. So, that is basically what I have got, and I have to apply the limits to this, and once I apply the limits to this, sin phi minus sin phi. And of course, the 2's all cancel out, and this is what you get. Now, what is going to be obvious over here is when you substitute, this is your sanity check, we said that if we substitute phi equal to pi by 2, we should get back our result for class B. So, if I substitute phi equal to pi by 2, sin pi by 2 is equal to 1, phi times cos phi, cos of pi by 2 is equal to 0. So, I basically get IRF by pi. Now, under this scenario, what is IRF? IRF is the amplitude of this sine wave, right, and the amplitude of that sine wave is going to be I max. So, basically I am going to get I max by pi, which is the old result. So, I am correct, right. So, this is my sanity check. Okay. So, what I have done so far is I have figured out what is the average ID. The next step is to figure out what is the fundamental component of ID, right. This is my next step. Average ID will give me an understanding of what is the power consumed. The power consumed is the average ID times VDD, because the average ID is what is the current coming through the RF choke. Now, I want to understand what is the fundamental of ID. So, how do you find out the fundamental of ID? You do a Fourier series. Okay, this is the expression for ID. Fundamental of ID is by doing a Fourier series. No, it is not IRF. It is not IRF. Do not worry. You do a Fourier series expansion, and that is what is going to tell you what is the fundamental component of ID. Okay, this is the way to do a Fourier series expansion. This is the first component, and of course, you replace capital T with something that relates to theta, and capital T is the period. So, that should be replaced by 2 pi, right. So, I am going to make the substitution okay. This is the substitution I am going to make, and as a result 0 will relate to 0, capital T will be relating to 2 pi, or you could shift your integration from minus T by 2 to plus T by 2, you could do that also. That I think will be helpful in our case. Cos omega naught T, omega naught is 2 pi by capital T, right. 1 by capital T is the frequency, 2 pi times that is omega. Right. So, I have done all these substitutions, and these substitutions lead me to believe that this is what I am doing. Right. let us remove these brackets. Now, ID of t, as before, ID is 0 for all other theta, and ID is something between minus phi and plus phi. So, this integral is just basically going to boil down to an integral between minus phi and plus phi, and between minus phi and plus phi, ID is something. It is IRF times cos theta minus cos phi. Right. Now, you break up this integral, it is a little involved. You have got cos square theta. Cos square theta is right. How do you know this is correct? 1 is cos squared plus sin squared, cos 2 theta is cos squared minus sin squared. So, you have got 2 cos squared theta, half of that. Okay. So, do not worry, it is not a lot of trigonometry. I mean, whatever trigonometry there is, you can actually work it out on the fly. All right. So, this is the integral that we are working on, and now you basically realize that there are 3 small integrals. The first one is a trivial integral, it is an integral of half. Integral of half is half times theta. So, half times 2 theta, applying the limits, you will get 2 phi, half times 2 phi, which is phi. Right. The second integral is half of cos 2 theta. Integral half of cos 2 theta d theta. If you think about this, you replace 2 theta with alpha. If you replace 2 theta with alpha, then twice d theta will be d alpha. So, basically what that means is you have got 1/4 of integral cos alpha d alpha. Agreed? Okay. Integral of cos alpha d alpha is sin alpha, right, and what are the limits over here? Limits are minus phi by 2 to phi by 2. All right. So, this is the second integral. The third integral No, I think I am making a mistake over here. Yeah. So, the limits are going to be from that is better 2 phi minus 2 phi to plus 2 phi, all right, which is basically going to become equal to sine of 2 phi minus sine of 2 phi. So, that is twice sine of 2 phi. So, this is what I am going to get. All right. And the third integral is of cos phi times cos theta d theta. There is a negative sign, remember that. So, cos phi times cos theta, cos phi is a constant, okay. Integral cos theta d theta is sin theta. Apply the limits phi to minus phi, you are going to get minus 2 sin phi cos phi. Right. So, this is the complete integral, and what do you see over here? Half of sin 2 phi is equal to sin phi times cos phi. Okay. So, I have compressed those two terms into one, and you can rewrite it in this fashion if you want to. So, this is the fundamental component of the current going into the MOSFET, which is the fundamental component of the current going into the load. What about the amplitude of the voltage at the load? Amplitude is VDD, right, same argument as before. It is the same argument as before. Supposing I have some fundamental of the current going into the load, this is the current going into the load. Okay. I would like its amplitude to be equal to VDD, the amplitude of the voltage to be equal to VDD, so that at the output the voltage is swinging all the way from plus 2 VDD to 0, right over here. Right over here, I am planning to allow the voltage to swing from 2 VDD down to 0. Right. This is the idea, which means it has an amplitude of VDD, and therefore, the power delivered to the load okay. And you compare this expression against this expression, which is VDD times that quantity, and what you are going to get VDD times IRF by pi, I think, will go away. All right. So, this is the efficiency that I have got, and if you look at this expression and compare it, plug in, first of all plug in phi equal to pi by 2, that is your class B, phi equal to pi, that is your class A. You should get back good old results. So, twice pi by 2 is pi minus sine of pi, sine of 0 degrees is 0, sine of pi is also equal to 0, divided by 4 times sine of phi, sine of pi by 2 is 1, minus phi times cos of phi, pi by 2 times cos of pi by 2, that is equal to 0. Okay. So, this is the same result as before. Where was I? All right. So, that is why I skipped the step of computing all kinds of things and doing so many integrals in the same class, right. Kind of makes you think less. So, we did one and can back calculate and prove that our assumption was correct. We did an I estimation, right, and said that looks like it is going to be half of the swing. All right. What about if phi is equal to pi? If phi is equal to pi, so I have got 2 pi minus sine of 2 pi is equal to 0, divided by 4 times sine of pi is equal to 0, minus phi times phi is pi times cos of pi, that is equal to minus 1. Okay. So, you get 2 pi by 4 pi, which is exactly equal to half. Remember, we did this in the previous lecture, right. The efficiency of a class A system is at max 50%. Why is this at max? Because of this. All right, you need a little bit of room to allow for the transistor to remain in saturation. So, little bit of room is needed over there. If you do not allow that room, then your device is going to cut off at a place where you do not want it to cut off, right. When the current is maximum, that is where the device is likely to cut off. Okay. So, this is the general expression for a class C amplifier, efficiency of a class C amplifier, and this kind of tells you that as you decrease the conduction angle. Okay. So, for a conduction angle of pi by 2, you get an efficiency of pi by 4. What if the conduction angle is pi by 4? So, twice pi by 4 will give you pi by 2 minus sine of 2 phi, 2 phi is pi by 2. So, sine of 2 phi is 1, divided by 4 times sine of phi, sine of pi by 4 is 1 by root 2, minus phi times phi is pi by 2, pi by 4, cos of phi is again 1 by root 2. So, if you do quick computation over here, pi by 2 is something like 1.55, 1.57 minus 1 divided by 4 times 1 by root 2 is 0.7 minus pi by 4 is pi is 3.1. So, 3.1 by 4 is how much? 0.77. .78 into 0.7. So, let us approximate it as 0.8. So, 0.56. So, it is a little more than 0.14. Okay. And 4 times 0.145 is some, I think it is about maybe 0.15. Which is very close to 100%, right. So, what do you see over here? I just made the conduction angle smaller and I got a better efficiency. What is going on over here? What is going on? What comes to your mind by saying that I am making the conduction angle smaller and I am getting better and better efficiencies? What is going on over here? Think about it. Think about it. What is the deal in this waveform? I am making, this is all that the current is. Okay, let us choose some other color over here. This is the current waveform, all right. Now, most of the time the current is 0. For a little blip of time, you have got some amount of current. That means that the average current drawn from the power supply, remember here we got an average current of I max by pi, that average current is dropping. If you conduct all the time, the average current is something, it is going to be I max by 2 or something like that. We are going down as far as the average current is concerned. What is the average current when the conduction angle is pi by 4? When the conduction angle is pi by 4, the average current is IRF by pi times sine pi by 4 is 1 by root 2. So, 0.7 minus phi, which is again pi by 4, something like 0.8 times 0.7. Okay. So, I have got something of the order of 0.15. Right. So, the average current is going down. I am getting lesser and lesser average currents by conducting for lesser durations of time. Now, when you are getting lesser and lesser average currents, what is happening to the power delivered to the load? The current delivered to the load is also going down. What does that mean? That means that the amount of power that you are delivering to the load is obviously also going down. So, you are going down in terms of the power consumed, you are also going down in terms of the power delivered, right. So, the sad news is that these class C amplifiers although it looks like you can achieve whatever efficiency you want, it looks like that by making the conduction angle narrower and narrower. The tragedy of the matter is that you end up delivering lesser and lesser power to the load. Your devices, everything is always off. So, of course, if everything is off, your efficiency is going to be 100%. No power delivered, no power used, efficiency is 100%, or tiny amount of power is used, tiny amount of power is delivered, right. So, this is the tragedy of the situation, and we have to deal with this. Now, with this I am going to close the lecture, and we are going to talk a little bit further about the class C amplifier and then about other amplifiers in the next lecture. Okay. Thank you.